Welcome to TalkTensors.
Glad to be here. We have a massive one today.
We really do. So I want you to imagine trying to make a human brain smarter, right? But instead of just growing a larger, denser frontal lobe, you just gave it 1 million separate microscopic auxiliary brains.
Which could query in like a fraction of a second.
Exactly. So today on the deep dive, we are looking at an architectural earthquake that basically proves the old bigger is better brute force paradigm is officially dead.
It really is. I mean, if you've been following the sheer panic around the compute wall lately, you know exactly what we're talking about.
Right, because scaling dense networks is becoming, frankly, physically and economically impossible. You, listening to this right now, are likely dealing with the reality of GPU shortages and, memory bandwidth limits.
Oh, absolutely. Everyone is feeling the squeeze right now.
Well, today we are unpacking a trending technology that completely shatters that bottleneck.
Yeah, we are looking at a fundamental rethinking of how a neural network stores and retrieves information. It's a massive pivot away from monolithic matrices
toward this hyper-fragmented dynamic routing system. So today's mission on our deep dive is to explore the parameter-efficient expert retrieval architecture, PEER.
Or, as the community is colloquially calling it right now, the mixture of 1 million experts.
Which is such a great name. We are going to uncover how scaling a network to include over 1 million tiny single neuron experts decouples model size from active compute cost.
Right. And to set the table for why this specific architecture is dominating the discourse right now, we kind of have to look at the anatomy of a standard transformer.
Specifically the feed-forward layers, right?
Exactly. The FFWs are essentially the factual memory banks of the model.
Okay.
They hold the world knowledge, the trivia, the relationships.
And they account for what, roughly 2/3 of a model's total parameters?
Yeah, about 2/3. And what PEER does is it just rips out the massive, dense matrices in those FFW layers and replaces them with a sprawling sea of microscopic experts.
And it navigates that sea using this hyper-efficient product key index, which we will get into. But okay, let's unpack this.
Let's do it.
Because to truly appreciate why 1 million tiny experts is such a revolutionary concept, we first need to understand the physics of the problem, right? We need to look at why dense models and even the traditional coarse-grained mixture of experts models hit a hard wall.
They absolutely hit a wall.
So let's start with the dense feed-forward layer. What is the specific mathematical trap that causes this compute wall?
Well, it comes down to the hidden layer width in a traditional dense transformer. If you want the model to memorize more facts or understand more nuance, you have to make that hidden layer wider.
You just add more neurons.
Right. You add more neurons, which means larger weight matrices.
Mm-hmm.
But the trap is that the computational footprint, the floating point operations per second, or FLOPs, scale strictly linearly with that parameter count.
And the activation memory too, right?
Yes, exactly. Both of them.
So if I double the parameters to cram in more knowledge, I am forced to double the compute cost for every single token that passes through that layer.
Yes, and that is just a brutal tax to pay. I mean, every single word you generate requires reading every single weight from high bandwidth memory into the compute cores.
Then you multiply them and write the activations back.
Exactly. It's a brute force approach.
Yeah.
You are paying the maximum possible energy cost to access the entire library of the model's knowledge.
Even if the current token only needs a tiny fraction of it. Like if I'm trying to buy a pair of socks, it's like having to walk through every single aisle of a massive department store just to check out.
That's a perfect analogy, actually. You're walking past the refrigerators and the TVs just to buy socks. Which brings us to the original MOE, or mixture of experts.
Right, we've talked about the architecture behind models like the switch transformers on the show before. The whole pitch of traditional MOE was to solve this linear scaling trap by introducing conditional computation.
Exactly. Traditional MOE, what we should probably now call coarse-grained MOE chops, that massive dense layer up into a smaller set of large experts.
Like a common configuration is 128 experts, right?
Right, 128 is standard. And each of those 128 experts is essentially its own standard multi-layer feed-forward network.
So it's like changing the department store into a mall with 128 big box stores.
Yeah. And when a token arrives in the layer, A routing mechanism steps in and says, hey, I only need to send this token to expert 12 and expert 47.
So you decouple the total parameter count from the active compute cost, you get a massive model, but for any given token, you only wake up and compute a fraction of it.
It sounds like the perfect solution.
It really does. But clearly, we wouldn't be doing a deep dive on a new architecture if the 128 expert paradigm didn't have its own massive flaw.
Yeah, unfortunately it does. The flaw is the routing bottleneck. It is basically the silent killer of traditional MOE scaling.
Let's get into the math of that bottleneck. If I try to scale from 128 experts up to, say, 1 million, what physically happens in the GPU?
So in a traditional MOE, the router is a neural network itself. It has to calculate a compatibility score for every single incoming token against every single available expert in the pool.
Wait, every single one?
Every single one. If you have 128 experts, the router performs 128 dot product calculations per token to figure out the best match. In computer science terms, this is an O of n operation.
Where n is the total number of experts.
Exactly.
Which means the cost of routing scales perfectly linearly with the number of experts.
Which is catastrophic if you want a massive number of them. I mean, if you attempt to scale to 1 million experts using a traditional router, the router has to perform 1 million calculations for every single token just to decide where to send it.
Just for the directory lookup.
Right. The computational cost of the router completely eclipses the feed-forward computation itself. It entirely wipes out the efficiency gains of using a sparse architecture.
Okay, I want to challenge this a bit because I know some early research tried to sidestep this entirely.
Okay, let's hear it.
If the learned router, the dynamic mathematical directory that requires a dot product for every expert, if that is the bottleneck, why are we forcing the model to dynamically learn where to send things via gradient descent?
I see where you're going.
Like, why not just use a deterministic hash table? We know that fixed hash tables have an O of 1 lookup complexity. It takes the exact same amount of time to find an item whether there are 10 items or 10 million.
Right.
I know a system called Mixture of Word Experts, or MOW, tried this exact thing. Why did the industry abandon that?
This raises an important question, and it's honestly the exact logical leap many researchers made early on. If the learned router is the O of n problem, just throw out the learned router and use an O of 1 hash.
Seems obvious, right?
It does, but here is the fundamental issue. Theoretical proofs and extensive empirical evidence have shown that fixed, non-trainable routers severely limit the expressivity and intelligence of the model.
Because language isn't static, I assume? A hash table maps tokens based on rigid rules.
Exactly. A token's meaning is highly contextual. The word bank in a financial document requires an entirely different set of factual parameters than the word bank in a hydrology paper about rivers.
Right, financial bank versus river bank.
Yeah. A fixed hash table maps the string of characters B, A, and K to the same expert every single time. But a learned router, which is trained via gradient descent alongside the rest of the network, identifies latent, hidden clusters in the data.
Oh, so it dynamically routes based on the contextualized hidden state of the token, not just the raw token ID.
Precisely. Learned routers filter out spurious directions and optimize the actual reasoning pathways. So we are stuck in this paradox.
We absolutely must have a learned router for high performance.
Yes, but a traditional learned router is strictly impossible to run efficiently if n is 1 million.
Wow. So we needed a breakthrough, which perfectly sets up the theoretical foundation of peer.
It does.
We know we need a learned router, and we know traditional coarse-grained MOE hits a ceiling. So how did the community figure out that the answer was making the experts microscopic and massively numerous?
To understand this, we really need to look at the fine-grained MOE scaling law. This was a pivotal realization in sparse modeling.
Okay, walk me through it.
Researchers basically asked, what actually dictates the scaling efficiency of an OE layer? And they defined it with a very specific granularity equation.
Let's break down the variables in this equation for the listener, because I think this is crucial.
Okay, there are 3 vital variables here. First, P, which is the total number of parameters in the model. This is your total storage capacity.
Got it. Total library size.
Yeah. Second, P active, which is the number of active parameters per token. This dictates your device memory limits and your computational FLOP cost.
The cost per word, basically.
Right. And third, P expert, which is the size of a single expert module.
Okay, so total size, active compute cost per token, and the size of the individual expert block. How do these relate to the concept of granularity?
Granularity, represented by a capital G, is defined mathematically as P active divided by P expert.
So active parameters divided by the size of one expert.
Yeah, it essentially represents the number of active experts you are calling upon for any given token. Now, the scaling laws dictate a harsh mathematical reality here. To improve the final performance of a model, to push perplexity down, you must scale up the total parameters P, and you must scale up the granularity G.
Okay, so you want a massive library, and you want to pull from many specialized sections of that library simultaneously.
Yes, but, and this is the core constraint that drives peer, you must strictly limit P active. You cannot let the active parameter to count inflate.
Because the moment you do, your memory footprint and inference latency just balloon, right?
Exactly. The memory cost of P active has to be multiplied by every token in a batch.
So we have this crazy physical standoff on the silicon. We want P, total parameters, to scale up infinitely. We want G, granularity, to go up, but P active must remain completely flat.
Right.
How does the math resolve that?
Well, you look at the equation. G equals P active divided by P expert. If P active is a fixed ceiling, the only mathematical way to increase granularity G is to make the denominator P expert incredibly small.
Oh, wow. You must shrink the size of the individual experts.
Exactly. And since the total parameters P equals the number of experts times the size of the experts, if you are shrinking the expert size, but demand the total parameters grow, the undeniable conclusion is that you need a massive, staggering number of tiny experts.
Millions of them. It is literally the only way the physics of the compute wall let you scale.
Yep. The math forces your hand.
And here's where it gets really interesting, especially when you think about the future of AI, not just as a static version-locked tool, but as a continuous entity. I am talking about lifelong learning.
Oh, this is my favorite part.
Why is having a million tiny experts the holy grail for a model that never stops ingesting data?
Because it solves catastrophic forgetting, which is arguably the most frustrating structural flaw in dense neural networks right now.
If I remember correctly, catastrophic forgetting is basically a model overriding its own hard drive, right?
That's a good way to put it.
Like, if I train a dense model on 2023 data, all the weights settle into a specific configuration. Then, if I want to update it with new facts from 2026, I have to run gradient descent over those same weights again.
Right, because the network is dense.
So adjusting the weights to learn the 2026 facts inadvertently alters the weights that were storing the 2023 facts. They share the same physical neurons. The model literally forgets the past to learn the present. Is that right?
That is exactly the mechanism. The weights are hopelessly entangled. It's like you're trying to write a new chapter in a book, but you only have one piece of paper, so you have to erase the previous chapter to make room.
But with an architecture of a million distinct, tiny experts, that paradigm changes entirely.
Completely. If you have an indefinitely long, continuous stream of data arriving daily, a massive MOE allows you to dynamically freeze the old expert.
Freeze them, permanently.
Yeah. The specific experts that learn the physics equations or the historical dates from the first round of training, you lock their gradients. They are permanent. As new data arrives, the router identifies that this is novel information and routes it to new, unused experts.
Or architecturally, you literally just append new experts to the pool.
Right, exactly. You maintain the model's plasticity, its ability to learn new things, without destroying its established stability.
That maps so well to biological intuition. When you, the listener, learn how to drive a car, you don't overwrite the neural pathways that allow you to ride a bike.
Right. Your brain doesn't have a single dense feed-forward layer that gets catastrophically rewritten.
No, it has highly specialized, localized pathways. This sprawling MOE architecture is pushing foundation models closer to that localized biological reality.
And if you are dealing with a never-ending data stream, you absolutely necessitate an expanding pool of experts. You need an architecture that can handle 1 million today and 10 million tomorrow without the compute footprint of a single forward pass changing it all.
Okay, so the theory is airtight. We know from the scaling laws that we need millions of tiny experts to push the total parameter count up without blowing up GPU budgets.
Right.
We know we need a learned router to find them, and we know this sparsity unlocks lifelong learning. Now, how does the peer architecture actually build this?
Let's get under the hood.
Let's start with the tiny part. What does an expert actually look like in peer?
This is where peer radically diverges from something like switch transformer. In a traditional MOE, an expert is a full-fledged feed-forward network. It has multiple layers, massive intermediate dimensions, huge matrices of weights.
Right.
In peer, Every single expert is a singleton MLP.
A singleton MLP. Wait, hold on. A single neuron.
A single neuron.
That's microscopic. I mean, a single neuron is basically just a linear transformation and an activation function. It's just drawing a mathematical line on a high-dimensional graph.
It is.
How can a single line understand the nuance of a highly contextualized language token? One neuron can't process meaning on its own.
You're right. It absolutely can't. A singleton MLP is profoundly weak on its own. It consists of just an up projection vector, a nonlinear activation like a ReLU or GELU, and a down projection vector. That is it.
So where does the power come from?
The power doesn't come from the individual neuron. The power comes from the dynamic assembly via multi-head retrieval.
Okay, explain the multi-head mechanism here.
So Peer doesn't just ask one query and retrieve one expert. It uses multiple independent query networks simultaneously. Think of them as multiple heads, similar to multi-head attention. A common configuration in the paper is using H equals 8 heads.
So there are 8 distinct query vectors being projected out into this sea of 1 million experts at the exact same time.
Yes, and each of those 8 heads doesn't just retrieve one expert. Each head retrieves a small neighborhood, say K equals 16 experts.
Okay, let me do the math. You have 8 heads, each pulling 16 single neuron experts. This means for any specific token, the routing mechanism retrieves a total of 128 distinct neurons.
Ah, I see. So instead of having a pre-built, rigid 1 in 28 neuron expert waiting for you like in traditional Mo, you are dynamically assembling a custom 128 neuron feed-forward layer on the fly, token by token.
Exactly.
You are pulling specific, isolated features from a shared repository of 1 million. It is entirely bespoke dynamic assembly.
That's incredible.
You linearly combine or sum up the outputs of these tiny experts weighted by their router scores. Because the hidden neurons are shared across a vast pool, it dramatically enhances knowledge transfer and parameter efficiency.
And I assume the nonlinear activation functions inside those retrieved neurons, the GELUs, allow the combined output to model highly complex nonlinear relationships, even though the building blocks are tiny.
Yep, you hit the nail on the head.
That is incredibly elegant. But it brings us right back to the $1 million routing bottleneck.
Right, the O of N problem.
We still have a pool of over 1 million of these singleton experts. If we have 8 heads, and each head needs to find the top 16 experts out of 1 million, how on earth are we doing this without the O of N math destroying our inference latency?
This is the magic trick.
How does Peer route to 1 million experts cheaply?
This is the true genius of the architecture, and it relies on a technique borrowed from an older concept called product key memory. The solution is product key retrieval.
Let's walk through product keys slowly, because this is the mechanism that makes the whole thing possible.
Okay, so in a naive routing system, if you have 1 million experts, you have 1 million distinct key vectors. A query vector comes in, and the GPU has to calculate the dot product between your query and all 1 million keys.
Exhaustive search.
Right. Product key retrieval completely sidesteps this by changing how the keys are mathematically constructed. Instead of having 1 million independent monolithic keys, Peer creates keys by concatenating vectors from 2 much smaller sets of subkeys.
Concatenating. So joining them end to end. Let's make this concrete.
Mathematically, it operates on a Cartesian product space. Let's say we want 1 million keys. The square root of 1 million is 1,000. So Peer creates 2 independent lists. Let's call them list A and list B.
Okay, 2 lists.
Each list contains exactly 1,000 subkeys. Each subkey is exactly half the dimensionality of a full key. To conceptually create the master list of 1 million keys, you take every subkey in list A and combine it with every subkey in list B.
1,000 times 1,000 equals 1,000 unique combinations.
Exactly.
Okay, I'm tracking the Cartesian product, but if you are still looking for one of those million combinations, don't you still have to search the million resulting keys?
No, and this is where the geometric properties of the dot product save the day. Because the final keys are concatenations, the dot product of a query with a final key is mathematically equivalent to the sum of the dot product of the first half of the query with subkey A plus the dot product of the second half of the query with subkey B.
Oh, wow. Wait, so you split the query vector itself in half.
Exactly. You send the first half of the query to search only the 1,000 subkeys in list A. You send the second half of the query to search only the 1,000 subkeys in list B. You find the top matches in list A, the top matches in list B, and you only combine those top matches to find your final experts.
Okay, let me try to visualize this with an analogy for the listener because this is mind-bending.
Go for it.
Imagine you are looking at a massive spreadsheet trying to find one specific cell out of 1 million cells. It's a 1,000 by 1,000 grid. The naive O of n way is to check every single cell one by one until you find the right one. A million distinct checks.
Right, very slow.
But the product key way is fundamentally different. Because the columns and rows are independent, you ask one question to find the top matching columns out of just 1,000 columns. Then you ask a second question to find the top matching rows out of 1,000 rows. You've only done 1,000 plus 1,000 checks.
Which is 2,000.
You've only done 2,000 calculations to instantly pinpoint the exact 1 in a million coordinate.
What's fascinating here is that your spreadsheet analogy maps perfectly to the sublinear complexity of the algorithm. You reduce the search complexity from O of n down to O of the square root of n.
That is just huge.
From checking 1,000,000 vectors to checking 2,000 vectors. It is a staggering reduction in computational overhead. And, mathematically, it is guaranteed that the top matching combinations from the independent subkeys will perfectly reconstruct the highest scoring overall keys.
That is wild. You entirely remove the routing bottleneck. You decouple the parameter count from the compute cost, allowing you to access 1,000,000 experts almost as cheaply as you could access a few hundred in a traditional MOE.
Yeah, you construct a massive sparse index structure that is fully learned and fully differentiable. The model still trains its subkeys via gradient descent, learning those latent clusters of concepts, but the retrieval process is hyper-efficient.
Okay, so the theory is beautiful, the architecture is elegant, we have single neuron experts and Cartesian product routing, but as we know, theory is just theory until it survives contact with real-world data sets.
Always.
I want to look at the empirical evidence. Does Peer actually outperform traditional models when the rubber meets the road? Let's talk about the isoflop analysis.
Isoflop analysis is the gold standard benchmark for this exact kind of architectural claim. ISO meaning equal, and FLOP being floating point operations. It is a rigorous way to compare architectures on a perfectly level playing field by locking the computational budget during training.
So no cheating by just throwing more A100 GPU hours at the sparse model to make it look better.
Exactly. You dictate that every model gets exactly the same amount of compute energy to train. In the Peer paper, they tested at two distinct massive budgets. A smaller budget of 6 times 10 to the 18th FLPs, and a larger budget of 2 times 10 to the 19th FLPs.
To give you an idea, you listening right now, that larger budget represents a highly non-trivial amount of physical compute time.
Very expensive. They then plotted the models on a graph where the horizontal axis is the model size, the parameter count, and the vertical axis is the validation perplexity on the C4 dataset.
And obviously, lower perplexity means the model is making fewer errors in its predictions. We want the curves on this isoflop graph to dip as low as possible.
Exactly. Down and to the right is the goal.
Let's list the heavyweights that stepped into the ring for this showdown. We have the standard dense networks. We have the coarse-grained MOE, which is the traditional 128 large experts. We have a model using product key memory, or PKM, which is the older architecture Peer borrowed the routing trick from. And finally, we have Peer itself. What does the Pareto frontier actually look like?
The isoflop curves clearly show Peer shifting the Pareto frontier downward and to the right. Given the exact same compute budget, the Peer architecture achieves the lowest compute optimal perplexity across the board. The very bottom of the Peer U-curve is lower than the bottom of every other curve.
Meaning it is unequivocally making better use of the compute energy it is given. It is structurally smarter per FLOP.
Yes. And they validated this beyond just the C4 dataset. They took the compute optimal configurations and evaluated them across a gauntlet of major language modeling benchmarks.
Like what?
Curation corpus, Lambda, the pile, and Wikitext. Across varied domains, from web scrapes to highly structured text, the compute optimal Peer models achieve significantly lower perplexity scores than the dense models, the MOE 128 models, and the PKM models.
Wait, I need to jump in here with a clarification. You mentioned it beat PKM product key memory, but we just established that Peer literally borrowed the Cartesian product routing trick from PKM.
We did, yeah.
If Peer is using PKM's own routing mechanism, why does Peer absolutely crush PKM in the benchmarks? What is the architectural difference?
That is a crucial distinction, and it comes down to the fundamental difference between retrieving static data versus retrieving dynamic functions. In the original product key memory architecture, the system retrieves static memory vectors.
Static vectors.
Right. The query goes into the index, finds a match, and pulls out a fixed string of numbers. Those numbers are just added to the residual stream.
It's like pulling a static flashcard out of a filing cabinet. The flashcard never changes, regardless of what the rest of the sentence says.
Precisely. But Peer doesn't retrieve static memory. Peer retrieves learned functions. It retrieves single neuron MLPs. When the query goes into the peer index, it pulls out an expert network. And because it's a network, its output dynamically changes based on the specific input token's hidden state.
Ah, so the retrieved expert actually applies a mathematical transformation to the input.
Yes, the retrieved expert takes the input state vector, applies its up projection, runs it through the nonlinear GELU activation, and down projects it. The output is highly contextualized to that specific moment in the forward pass.
That makes total sense.
Retrieving an input-dependent function is vastly more expressive and powerful than retrieving a static memory vector, even if they use the exact same Cartesian routing mechanism to find it. That is why peer outperforms PKM so drastically.
It's the difference between looking up a static fact in an encyclopedia versus hiring a specialized consultant to analyze your specific problem. The encyclopedia gives everyone the same paragraph. The consultant actively computes a tailored solution based on your exact variables.
That is a very accurate way to conceptualize the difference between memory vectors and dynamic single neuron functions.
So the benchmark results are stellar, but to truly understand why researchers are so excited about this, we have to look at the ablation studies. What happens when the researchers started twisting the dials on this architecture?
The ablations are where it gets fun.
Let's start with the big one. Scaling the total number of experts, the N dial. If we just keep adding kiosks to this mall infinitely without slowing down the routing, did they push that to the limit?
The ablation study on N is particularly revealing. They held the computational budget and the active parameter count steady, and they simply increased the total number of available experts in the latent pool.
How high did they go?
They scaled from roughly 16,000 experts up to 65,000, up to 260,000, all the way up to 224 squared, which is over 1 million experts.
And what happens to the perplexity?
The isoflop curve steadily interpolates downward. Simply increasing the sheer number of latent experts in the repository consistently improves the model's final performance without ballooning the inference compute cost.
That's incredible.
The model literally gets smarter just by having a larger latent library to draw from because the routing is sublinear.
What about the other dial? The HK dial, the number of active experts retrieved per token. We established earlier that granularity G equals HK. If you retrieve more experts per token, if you dynamically assemble a 512 neuron layer instead of a 128 neuron layer, do you get a smarter model?
Yes, up to a point. They systematically varied the number of active experts retrieved, 32, 64, 128, all the way to 512 active experts per token. The results show that increasing the active experts generally leads to improved performance. It allows the model to dynamically assemble a more complex expressive neural network for that specific token. However, the performance gains eventually saturate. The curve flattens out.
And I imagine the memory bandwidth police show up at some point.
They absolutely do. Remember, every time you increase the number of active experts, you are directly increasing device memory consumption and MLPs. You are physically reading more vectors from high bandwidth memory into the SRAM and performing more summations.
Right, so you can't just scale that infinitely.
No. So in practice, an engineer deploying peer has to make a calculated trade-off. You find the sweet spot where expressivity is maximized before the memory bandwidth bottlenecks your GPUs.
Okay, this brings me to a notorious structural issue in the world of MOEs, the dead expert problem, or routing collapse.
Oh yeah, the classic failure mode.
If you have 1 million experts sitting in a virtual warehouse, isn't there a massive gaping risk that the model just gets lazy? What stops the router from finding a mathematically good enough path using the same 5,000 experts for every single token and leaving 995,000 experts gathering virtual dust? Because if you have 1 million experts and the model only uses 1% of them, you are just wasting memory storage.
Routing collapse is the bane of MOE training. It's a vicious feedback loop. The router randomly favors a few experts early in training. Because those experts are selected, they receive gradients and update their weights, becoming better at their jobs.
While the others just sit there.
Exactly. The unselected experts receive no gradients, so they remain randomly initialized. In the next forward pass, the router obviously prefers the trained experts over the random ones. The loop solidifies, and 99% of your capacity dies.
So how does peer, with a staggering 1 million experts, prevent routing collapse? How do you force a network to explore 1 million options?
The paper introduces a surprisingly simple, yet profoundly effective geometric solution: query batch normalization.
Batch normalization, a classic technique. But how does it apply to a Cartesian router? How does it actually work geometrically to save the experts?
They add a batch normalization layer directly on top of the query network, right before the queries are split and sent into the product key index. To understand how it works, visualize the latent space of the subkeys as a high-dimensional sphere.
Okay, a sphere.
Without normalization, as the query network trains, all the query vectors might start pointing in the exact same direction, clumping up in one tiny narrow cone on that sphere. If all queries point the same way, they all retrieve the exact same subkeys.
That's the collapse.
Exactly. What batch normalization does mathematically is subtract the mean of the batch and divide by the standard deviation. Geometrically, this takes that clumped up cone of query vectors, centers them perfectly at the origin of the latent space, and forces them to spread out with unit variance.
Oh, wow.
It physically stretches the queries across the entire sphere, forcing them to interact with a much wider distribution of subkeys.
It forcibly scatters the queries across the index so they can't be lazy.
And the empirical metrics on this are astounding. The researchers tracked an expert usage metric, the fraction of experts actually retrieved during inference over the validation set. Even with over 1 million experts, when query batch normalization is applied, the expert usage hits an astonishing 100%.
100%. Wait, it actually utilizes every single one of the 1 million microscopic experts? That is incredibly hard to do in sparse models.
Every single one. And they went further. They didn't just measure if an expert was touched once. They measured how evenly the load was distributed using the Kullback-Leibler divergence.
The KL divergence.
Right. KL divergence measures how one probability distribution differs from a second, reference probability distribution. Here, they calculated the divergence of the actual expert routing distribution against a perfectly uniform flat distribution.
So a lower KL divergence score means the routing load is perfectly balanced, like water finding its level.
Precisely. This is called the unevenness metric. When they applied query batch normalization, the unevenness metric dropped precipitously. The routing load isn't just utilizing all experts, it is beautifully and efficiently balanced across the entire massive repository. No single expert is overloaded, and no expert is starved.
So what does this all mean? Let's synthesize this for the practitioners listening. We are looking at an architecture that allowed you to scale the parameter count of the sheer factual knowledge base of a foundation model into the stratosphere.
Yeah.
You can have millions of parameters sitting latent, but because you're using Cartesian product key retrieval, the routing bottleneck is mathematically bypassed. And because the experts are single neurons dynamically assembled via multi-head attention, the active compute cost remains flat.
It's brilliant.
And finally, batch normalization geometrically ensures the entire network is actually utilized. This proves that foundation models can keep absorbing the fine-grained scaling law without requiring a linear explosion in the physical compute clusters required to run them.
If we connect this to the bigger picture, peer is the bridge we have been looking for. It bridges the gap between the insatiable desire for massive parameter scaling and the harsh physical limits of silicon and memory bandwidth. We are officially moving away from monolithic, dense blocks of compute toward highly specialized, dynamically assembled, hyperfragmented networks.
It's a total paradigm shift. And that brings us to the novel notions segment.
I'm ready. I love this part.
Now, a quick disclaimer for our listeners. The following segment is for entertainment purposes only. We are taking the rigorous architecture we just discussed and projecting it outward into outlandish but logically consistent future scenarios.
So don't go writing a paper on this just yet.
Right. We are asking, based strictly on Peer's trajectory, what wild realities could this unlock? I am pitching the concept of the immortal century scale foundation model.
The immortal model. Okay, break down the mechanics of how Peer enables that.
Right now, the life cycle of an AI model is discrete and episodic. A lab spends $1 billion in a year of compute to train a dense model from scratch. It's locked. Then they do it again 2 years later. It is a massive undertaking precisely because of the dense architectures and the catastrophic forgetting we discussed earlier.
Well, you can't just keep updating it.
But Peer changes the physics of data ingestion because Peer allows for an infinitely expanding pool of single neuron experts without altering the compute footprint of a forward pass. We could see the birth of a single, continuous, non-expiring AI model that literally lives and updates for decades.
Continuous lifelong learning at a civilization scale. That is a wild thought.
Exactly. Instead of training distinct versions, a consortium just launches the model. And it never stops. As new daily data streams arrive, news from 2026, scientific breakthroughs from 2030, geopolitical shifts in 2036, the system simply dynamically appends new product subkeys and new Singleton MLPs to the periphery of the peer layer.
And you leverage the gradient freezing mechanism. The experts that memorize the foundational logic of mathematics or the historical events of the 20th century are permanently locked in the sparse index.
Yep.
They're never subjected to gradient descent again, so they never experience weight degradation.
Exactly. The model experiences true lifelong learning. It perfectly silos 2026 facts from 2036 facts. The model becomes a flawless, time-stamped historical ledger of human knowledge. If you ask it a question about a 2024 event, it dynamically routes to the specific single neuron experts forged in 2024. If you ask it about a 2040 event, the Cartesian keys route it to the 2040 experts.
Architecturally, this would fundamentally alter the economics of the AI industry. You no longer have these massive, risky, all-or-nothing training runs that take months to debug. You transition to a continuous, low-level burn of compute that just perpetually expands the sparse index. It's a compounding asset.
And because the forward pass complexity is sublinear, thanks to the Cartesian product keys, a model with 1 billion experts wouldn't be noticeably slower to query than a model with 1 million.
The inference cost stays flat while the intelligence compounds over a century. I think it is a highly plausible evolution of this sparse architecture.
It raises fascinating logistical questions. If a model is a continuous ledger, how do you excise obsolete data without retraining? Do you just delete the subkeys pointing to the outdated experts?
That's a good question. Computationally, though, the peer system makes the immortal model structurally viable for the first time.
It's a brave new world of sublinear routing. And with that, we have to wrap up today's deep dive. But I want to leave you, the listener, with a final provocative thought to mull over as you go about your day.
Always a good way to end.
Think about the physical trajectory we just mapped out. From a single dense brain to 128 large experts to 1 million single neuron experts dynamically assembled on the fly. As this granularity scales, if a neural network can eventually store billions of distinct single neuron functions that are perfectly routed in milliseconds, at what point does a single AI stop being a unified model and start becoming an entire decentralized economy of microscopic algorithms?
That is a lot to think about.
Thank you for joining us on this deep dive into the architecture that is reshaping the compute wall. Think about how this changes the future of scaling, and we will see you next time on TalkTensors.